In this video, we are going to learn how to solve equations involving a single trigonometric function. For these three examples on the left, we're going to solve each equation, give a general formula for all the solutions, and then list 6 solutions. Now, the reason why we're going to need to give a formula for all of these solutions is because these functions are all periodic. We saw in the graphs that they repeat the same patterns over and over again over their domain. So we need to create a formula to list every single possible solution. So starting with this first problem, cosine of theta is equal to 1/2. The way we should go about solving it isn't necessarily taking the cosine inverse of the other side, because that would only yield one solution. We're actually going to imagine where on the unit circle is cosine of theta equal to 1/2, which happens at this angle up here, where the x-coordinate is 1/2, as well as straight down over here, where x is equal to 1/2. So these two angles on the unit circle are at pi over 3 and at 5 pi over 3. So those are two such angles. So theta is equal to pi over 3, and theta is equal to 5 pi over 3. Now, these are periodic functions, so not only is this angle pi over 3 a solution, I could have rotated a whole revolution and then an extra pi over 3, and that would have been a solution as well. And I could have done 2 full rotations and then landed on that angle and gotten another solution. I can do as many revolutions as I wanted to, and as long as I end in this general area of my rotation, in this exact area, then the solution will equal 1/2. So the way we adjust for this is we add the period of the trig function times k to both solutions, where k is an integer. So I'm going to highlight this with a red pen, because this each 2 pi is 1 revolution, and I can add as many as I want. And if I use a negative k value, I'll actually rotate the opposite direction and then subtract, and then land on the angle I want to. So I can rotate in either direction. So to find more solutions, I can allow k to equal -1. By doing so, I would subtract 2 pi from pi over 3, which would give me -5 pi over 3. And I could subtract 2 pi from 5 pi over 3, which would give me -pi over 3 for those two particular examples. And what that would be is pi over 3 was rotated, instead of going up pi over 3, I would go down pi over 3, which would land me right here in this area, which is a different rotation from going counterclockwise. So that is a different solution. And same thing here, -5 pi over 3 is rotating this much counterclockwise, but doing it clockwise now, which would land me where the pi over 3 angle is. Now, if k was equal to 0, I would get the solutions pi over 3 and 5 pi over 3 if I don't rotate, which are the initial solutions I found. And if I allow k to equal 1, I would add pi to pi over 3, which would be 7 pi over 3. And then 2 pi plus 5 pi over 3 is 11 pi over 3. All 6 of these are solutions, and as long as we just change that integer value for k, we could find more and more if we wanted to. So I'm going to stop there. So these will be your general formulas with the k, while these are just 6 possible solutions, with there being an infinite number of solutions here. Let's try this again, but with tangent of theta. So where is tangent of theta equal to -√3 over 3? That would be over here in this, in the 4th quadrant and in the 2nd quadrant. Now, what's nice about tangents is that its solutions are pi apart already. So we could identify both of these angles as being 5 pi over 6 and 11 pi over 6. That's the two possible angles that make tangent of theta negative square root 3 over 3. So I would have theta is equal to 5 pi over 6 and 11 pi over 6 plus, but this time instead of 2 pi, the period of tangent isn't 2 pi, it's pi, so I always do plus pi k. Now, in this respect, these two angles are already pi apart. So it's redundant to put both of these formulas. I would just need one of them. And it doesn't matter which one you pick. I like to pick the smaller angle of the two. And I would get just 5 pi over 6 plus pi k would be my general formula for this solution. And if I want to get more solutions, I make k different values. So, for example, if k was negative 2, I would take away 2 pi from 5 pi over 6, which will leave me with negative 7 pi over 6. And if k was negative 1, I would take away 1 pi from 5 pi over 6, give me negative pi over 6. K could be 0, and I'll get 5 pi over 6. And if I keep just adding pi over and over again, I'll find as many more solutions as I would like. Which, by the way, I'm just adding 6 pi over 6 is how I'm counting this so well. So this next one would be 17 pi over 6. And another one would be 23 pi over 6. And that would be 6 solutions that you could use. And lastly, I have cosecant of theta over 2. Now for this solution, I'm often not great at remembering what the value of cosecant is, but I always remember what the value of sine is. So the formula to convert cosecant to sine is that cosecant of theta is equal to 1 over sine theta. So they're reciprocals. So I can rewrite this equation as sine of theta over 2 is equal to negative 1 over the square root of 2, which when you rationalize that denominator is negative square root 2 over 2, which would happen in the third quadrant and the fourth quadrant. Which would be 5 pi over 4 and 7 pi over 4. Now you may be wondering what's going to happen to the theta over 2. We'll learn what happens when we make these general formulas. Because one formula would be theta over 2 is equal to 5 pi over 4 plus, again, the period of sine is 2 pi k. And the other formula will look like theta over 2 is equal to 7 pi over 4 plus, again, the period of sine is 2 pi, so we put plus 2 pi k. And if I want to finish solving this to get rid of the over 2 that's underneath the theta, I'll multiply each side of the equation by 2. So that'll give me theta is equal to 5 pi over 2 now when I multiply by 2 plus 4 pi k. Which makes sense because whenever you have 1/2 theta, your period would change to 4 pi. And over here, I would have 7 pi over 2 plus 4 pi k. And those would be my general formulas. And if I want to list out 6 solutions, I can use negative k, which is subtract 4 pi from 5 pi over 2, which is subtracting 8 pi over 2. So I could also get negative 3 pi over 2 and negative pi over 2. Using 0 for k, I can get 5 pi over 2 and then 7 pi over 2. And if I use 1 for k, which would be like 8 pi over 2 instead of 4 pi, I can get 13 pi over 2 and 15 pi over 2. But as you're seeing here, this can be very exhausting to have to like list out so many solutions every time for these functions. So as a general rule of thumb, when we're solving trigonometric equations, we'll sometimes just stick to 0 to 2 pi, which is one revolution. So we don't have to add this 2 pi k. We just list everything that would be on the unit circle. Again, we're not equaling 2 pi because 0 is already there. We don't need to have a double angle. So if I were to solve an equation on the interval, I'd first have to get the trig equation by itself. So I would subtract square root of 3 and then divide by 2. And I would find what angles on the unit circle would give me negative square root of 3 over 2 for sine, which would happen at 5 pi over 3 as well as 4 pi over 3 in the third quadrant. They have the same y value, and since I'm not worried about getting these periodic solutions, my solutions will just be 4 pi over 3 and 5 pi over 3. And it really lessens the work you have to do. Here, if I was doing secant squared, I would have to get secant by itself, so I would add 4 to each side, divide by 3. Give me 4/3, and then I would take the square roots of both sides. Give me secant of theta is equal to plus or minus 2 over root 3. Now again, I don't always remember what the value of secant is, but I do know that secant is the reciprocal of cosine. So I know that this could equal cosine of theta equal to plus or minus the square root of 3 over 2. So I'm looking everywhere where cosine would either be positive square root of 3 over 2 or negative square root of 3 over 2, which would happen at pi over 6, 5 pi over 6, or 7 pi over 6, or 11 pi over 6. These will all give you either a positive square root of 3 over 2, which would be at pi over 6 and 11 pi over 6, or it would be at negative square root of 3 over 2, which would be at 5 pi over 6 and 7 pi over 6. So all 4 of those would be solutions. So pi over 6, comma 5 pi over 6, comma 7 pi over 6, comma 11 pi over 6. And again, I don't have to do the periodic solutions because I'm stuck between my interval, but if I had to, all 4 of these would just have a plus 2 pi k when I solved it. And lastly, we'll do cotangent of theta minus pi over 2. We saw what happened when we had just a coefficient, but now what we do if we see that we have addition or subtraction inside of the trig function. Well, first, I'm going to use the fact that cotangent of theta is the reciprocal of tangent of theta. Just help me rewrite this equation. So I can write this as tangent of theta minus pi over 2 is equal to the reciprocal of 1, which is still 1. So where is tangent equal to 1? That would be in the first quadrant at pi over 4. In the first quadrant at pi over 4. And in the third quadrant at 5 pi over 4. So theta minus pi over 2 would equal pi over 4, or theta minus pi over 2 would equal 5 pi over 4. So to finish solving, I would add pi over 2 to each side, which would give me 3 pi over 4 and 7 pi over 4 as my 2 solutions. And those are still within my domain for theta. And if one of them happened to go outside of the range, I might consider maybe I've now shifted too far around, because here I shifted from pi over 4 to 3 pi over 4 and 5 pi over 4 to 7 pi over 4. So if one of these was at, like, for example, 9 pi over 4, I might consider the angle at pi over 4 as the answer instead. And that is how you solve equations involving a single trigonometric function.